Welcome to this explainer. Okay, today we're stepping right into the high-stakes world of an elite pastry masterclass, and we're looking closely at a really fascinating source detailing the alchemy of baking. Picture this. You're in a modernist pastry kitchen. The lighting is focused, the environment is pristine, and you are looking at a high-gloss, crystal-clear fruit insert. You take a professional surgical knife and slice right through it, creating this perfectly geometric, razor-sharp edge without a single drag or hint of friction. Achieving that perfection isn't actually about the flavor. The ultimate challenge in modern plant-based baking is mastering texture and structure. And, well, we are going to solve that challenge today. Okay, let's dive right into this. We're going on a little journey today, zooming all the way from the pastry kitchen down to the microscopic matrix. We'll start with the plant-based structure problem, take a deep dive into marine origins, look at material forms and precision, and finally, get into the physics of gelation.
All right, part one, the plant-based structure problem.
So in the traditional culinary world, if you wanted an elite dessert to hold perfectly on the counter, you relied on animal-derived gelatin, right? But with today's custom dietary requirements and shifting market demands, that's just, well, it's often not a viable option anymore. Usually someone chimes in and says, hey, just use Agar Agar instead. But here's the really critical question. Why do 90% of bakers completely fail when they try to use it?
If you've spent any time in a professional or even an amateur kitchen, you've probably seen the absolute heartbreak of this failure. The moment your beautiful glaze cools down, it turns terribly dull. That delicate mousse you spent hours on, it becomes rubbery and just hard. Or maybe the absolute worst, you slice into your perfectly layered insert and find these weird microscopic knots and lumps left inside. So why does this happen? Well, it happens because bakers treat this ingredient like it's just a cheap, direct swap for gelatin instead of actually understanding its unique mechanics.
Moving right along to part two, a deep dive into its marine origins.
To really get this ingredient, we actually need to zoom out of the kitchen and travel down to the deep ocean floor. Agar Agar isn't some synthetic laboratory powder, no. It's a completely natural, 100% plant-based hydrocolloid, and it's extracted from two very specific marine botanical groups of red seaweed, Jellidium and Gracilaria. This exact botanical extraction is what gives it such incredible natural strength. Now, locked tight within the cell walls of these specific seaweeds is a structural polysaccharide created by nature, and it's made of two critical components. On one side, you have agarose. Think of this as the main driving engine. It's what actually builds that rigid, solid gel network. On the flip side, you have Pectin, which steps in to provide that network with some much-needed flexibility and stabilization.
When you put these two together, they unlock three downright amazing physical superpowers for the baking industry. First off, it's an unmatched gelling agent, capable of giving any liquid a rigid, crystalline texture. Second, it's got incredible thickening power. It can easily increase viscosity even at super low concentrations. And third, it acts as a stabilizing matrix, which brilliantly prevents any separation in your delicate suspensions and emulsions.
But honestly, here is its absolute ultimate superpower. It is 100% odorless and tasteless. I mean, think about why that matters for a second. It means you can fold it into premium fruit juices, high-grade dairy creams, or super delicate botanical liquids, and it's going to lock in that rigid texture without disturbing the original organic flavor profile by even 0.01%. It's totally invisible to the palate, and that is exactly why it forms the primary infrastructure for international standard layered desserts.
All right, part three, material forms and precision.
Now, what's really interesting here is how the physical form of this ingredient completely changes what it can do. When you're sourcing supplies for a commercial kitchen, you'll see a few different options. First, we have strips, or bars. This is the most raw, traditional form, literally made by freezing and drying the seaweed gel. Because they have such a massive surface area, they dissolve the slowest. We're talking hours of soaking in water before you can even boil them. So obviously a pretty poor fit for a high-speed commercial setup. Next up, you have flakes. These are just mechanically crushed strips. They're a little bit better, but they carry a huge risk. If the center of a flake doesn't fully hydrate, you end up with these highly visible translucent dots that totally ruin the customer's mouthfeel. Finally, we have powder. The gel goes through these high-speed rotary milling machines that convert it into microscopic dust components. This gives it the absolute highest surface-to-volume ratio possible.
And that is exactly why Agar Agar powder is considered the absolute gold standard for modern pastry chefs. Because it's this microscopic dust matrix, it disperses perfectly and evenly in cold liquid without clumping, and it dissolves the fastest and the cleanest on the heating plate. Bottom line, if you want absolute precision, you literally only use the powder.
Okay, let's get into part four, the physics of gelation.
We're going to zoom all the way down to the thermodynamic molecular level now. Because really, understanding this structural shift is the absolute key to flawless execution. The gelling behavior of Agar Agar relies on this mind-blowing thermodynamic phenomenon called thermal hysteresis. Simply put, thermal hysteresis means there's a massive temperature gap between the point where a substance melts and where it actually sets into a gel.
Let's walk through how this builds across 3 molecular phases. Step 1 is the solid state. When you whisk the powder into cold liquid, its long carbohydrate polymers are tightly coiled up, kind of like unrolled ropes. They aren't really connecting at this stage. Step 2 is heating. The thermal kinetic energy literally breaks those tight coils, forcing the polymer chains to completely straighten out. And then, step 3, the cooling phase. As the temperature drops, those beautifully straight chains begin to cross-link, wrapping tightly together.
To achieve that second step, the heating phase, you have to hit exactly 85 degrees Celsius. This is the thermal activation point. It's the absolute minimum temperature you need for the kinetic energy to actually straighten those chains out so they can evenly distribute into the liquid solution.
So the crucial part is what happens next during cooling. The real magic happens precisely between 35 and 40 degrees Celsius. This right here is the critical setting threshold. At this exact temperature, the cross-linking violently locks the structure into place right at room temperature, meaning no way, you don't even need immediate refrigeration to form your gel.
And this brilliantly illustrates our final architectural lock, the 3D microscopic cage. Those straight chains wrap around each other to form this solid network grid. All the water molecules from your liquid, they are now physically trapped inside the empty spaces of this grid. The liquid completely loses its fluidity and transforms into a beautifully firm, incredibly stable hydrogel.
Finally, part 5, the architectural horizon.
So, in this explainer, we've journeyed all the way from the ocean floor to truly understand this marine polymer. We've looked at why powder reigns supreme, and we've broken down the thermodynamic physics of that microscopic cage. But understanding the raw skeleton, that's only half the engineering. As a pastry chef diving into actual real-world application, you still have to ask, what are the exact formulation ratios? How does this chemically differ from gelatin on a structural level? And most importantly, what are the 5 fatal mistakes bakers make that cause their premium products to just completely collapse right there on the counter? Well, we are going to uncover all of those advanced operational matrices in part 2. Until then, stay curious.
Welcome back, professionals. You're tuning into part 2 of our advanced Agar Agar Masterclass, right here in our Alchemy of Baking series. Now, in part 1, we really unpacked the botanical backbone and the molecular gelation chemistry of this specific hydrocolloid. But let's be real for a second. When you step onto the actual operational battlefield, a busy commercial kitchen with intense ticket pressure and high-end aesthetic demands, theory alone simply won't save you. You need applied chemistry. So today, we're taking that high-stakes molecular theory and slamming it directly into the pastry engineering of the real world.
To totally dominate this subject today, we have a very strict syllabus. We'll hit the operational battlefield, the professional dosage chart, the agar versus gelatin face-off, the troubleshooting protocol, and finally, expert pastry applications. Get ready for absolute technical precision.
All right, section 1, the operational battlefield, precision over theory.
Moving right along to section 2, the professional dosage chart, focusing on mathematical ratios.
Okay, let's dive right into this. In a professional setup, the stakes are incredibly high, and honestly, guesswork just creates massive disasters. If your measurement deviates by even 0.5%, your gorgeous Entremet suddenly becomes a weeping watery mess, or worse, an uncuttable block of rubber. You never ever scale agar by volume or with cups. Your dosage is strictly a percentage of your pure liquid weight. So, let's break this down into a rule of 3 for dosage ranges. For delicate custards or fluid gels where you just need a stable viscosity, you want to stay low, right between 0.2% and 0.5%. Now for standard ambient jellies that require really clean geometric cuts that dissolve smoothly, you bump that up to 0.7% to 1.0%. And for high-standing, rigid inserts built to survive hot climates, you push it to 1.2% to 1.5%. Anything beyond this bracket, and you're basically turning your dessert into an edible plastic.
Once your dosage is totally locked in, your next major rule is temperature. This number right here, 85 to 100 degrees Celsius, is completely non-negotiable. Look, agar will dissolve in cold water, sure, but it will absolutely not activate. Its mandatory activation threshold requires a full-on rolling boil. You literally have to hit this exact window on the boiler to shatter those microscopic particles and properly deploy the polymer network.
And just as that activation window is critical, the setting window is incredibly urgent. The exact setting temperature is between 35 and 40 degrees Celsius. In a practical sense, this means as soon as you pull your liquid off the stove and it drops to 50 degrees, boom, that is your final pouring window. If you hesitate there, immediate crystallization starts happening right inside the pan, which locks up the structure and permanently destroys your dessert's flawless mirror finish. You cannot save it once it starts.
Which brings us to Section 3, the agar versus gelatin face-off. Let's look at the ultimate comparison.
Let's see how this actually builds out practically, because there is massive confusion on the kitchen floor when chefs try swapping these two, and there is a major structural contrast between them. Looking at the matrix here, agar is a 100% plant-based marine red seaweed, which makes it completely vegan. Gelatin, on the other hand, is animal-derived collagen. Structurally, agar gives you a firm, somewhat brittle structure that snaps super cleanly under a knife. Gelatin yields an elastic, rubber-like, chewy texture. But the absolute biggest differentiator? The melting point. Agar remains solid all the way up to 85 degrees Celsius, making it exceptionally heat-resistant. Gelatin melts at just 35 degrees, which is body temperature. That gives gelatin its famous melt-in-the-mouth feel, but it also means it will completely collapse without strict refrigeration.
Because of this intense structural superiority, you absolutely must memorize this golden rule of conversion. 10 grams of gelatin equals 1.5 to 2 grams of pure agar-agar powder. I am stating this with absolute authority here. Agar is nearly 5 times more powerful than gelatin. You should never, ever replace them on a 1-to-1 ratio. If an international recipe calls for gelatin, you have to apply this mathematical reduction factor immediately, or your whole batch is ruined.
All right, Section 4, the troubleshooting protocol. Time to fix those kitchen failures.
Let's step into the diagnostic portion of this masterclass. Massive production losses happen in large kitchens purely due to simple chemical misunderstandings. Let's look at 4 critical mistakes. Mistake number 1. Dumping powder directly into hot liquid. If you drop agar straight into boiling puree, you get what's called microscopic encapsulation. Basically, the outside of the polymer seals up from the heat, creating a thick wall that leaves the inside totally dry. The result? Heavy, nasty lumps. The fix is super simple. Always whisk your dry agar powder into the cold liquid portion of your recipe first to hydrate it, and then take it to the heat.
Mistake number 2 is what we call the acid crash. Chefs often make the mistake of boiling agar directly with citrus fruits, things like passion fruit, lemon, or kiwi. The low pH and high acid profile of these fruits violently breaks down the agar's delicate polymer chains. So the fix here? Isolate the activation. Fully boil and activate the agar in a neutral liquid first, like a water-sugar syrup. Then, after you've turned off the heat, gently fold in those acidic fruit purees right at the very end.
Moving on to mistake number 3, incomplete activation, which I personally like to call the raw trap. Simply warming up the liquid and walking away is a classic amateur mistake. If you do that, the hydrocolloid just remains dormant and your dessert will literally never set. The fix here demands strict heat discipline. Bring that liquid to a full rolling boil. Set a timer and boil it continuously for strictly 60 to 90 seconds. You have to do this to fully deploy every single particle.
And finally, mistake number 4, eyeballing measurements with household spoons. Thinking to yourself, oh, I'll just add a spoonful, is incredibly dangerous. As we just learned, agar is extremely powerful. The fix is to strictly enforce professional standards. You absolutely must use a 0.1 gram precision microscale for your pastry management. Even a tiny 1 gram deviation will completely spoil the texture and stability of your final product.
And that brings us to Section 5, Expert Pastry Applications, High-End Engineering.
This is the fun part, where we actually translate all those precise chemical equations and perfectly calculated temperature rules into flawless, real-world dessert components. Applying our rule of 3 one more time, here are the ultimate applications. First up, high-gloss mirror glazes. Agar powder is literally the heart of neutral glazes. It sticks uniformly to vertical cake corners and freezes into this stunning, sweat-free mirror shine. Second, clean-cut multi-layered inserts. At exactly a 0.8% dosage, you get perfectly defined internal geometric fruit layers that hold sharp integrity, no bleeding whatsoever when you slice into them. And third, plant-based vegan mousses. Instead of relying on heavy animal collagen, you use a slow-flowing 0.3% activated agar stream, pouring it right into whipped plant creams. The result? Featherlight aeration with absolutely perfect architectural standing structure. It's beautiful. So what is the ultimate takeaway from this whole deep dive? It's all about zero-error professional execution. Over this really intense journey spanning parts 1 and 2, we've completely locked down everything, from this hydrocolloid's botanical backbone to its extremely precise industrial calculations, all the way to troubleshooting protocols. This is exactly how you transform from someone who just knows the theory to a master who absolutely dominates dessert structure using pure science.
Now, professionals, it is time for you to choose your next challenge. What is your next operational battlefield going to be? Do you want to master the precise science of pectin engineering next, or is your focus more on sugar art stabilization? Think about it, type Alchemy Chemist right down in the comments, and let me know your choice for our next advanced industrial module. Take this knowledge, elevate your engineering, refine your formulas, and I will see you in the next explainer. Keep baking and keep dominating the structure with science.